This past week has felt like Christmas has come early for us astrophysicists all around the world because the Dark Energy Survey has released 3 years worth of its observations of the sky, cataloguing over 226 million galaxies. Not only that, but they've also released 30 scientific papers describing all of those observations and analysing the data, and essentially that's what I've been doing for the past week. I have just been reading all of those, just digesting everything they've found, trying to pick out some of the really cool results that I want to highlight to all of you, because there has been some really intriguing findings, especially on the nature of dark matter and the nature of dark energy. All right, let's start with what actually is the Dark Energy Survey. We'll get to what actually is dark energy later in the video, but let's start with the Dark Energy Survey, or DES. It's a collaboration of over 400 astrophysicists worldwide, whose main goal is essentially to map out the positions of as many galaxies as possible as they can in the universe. To do that, they use the Blanco 4-meter telescope at the Cerro Tololo Inter-American Observatory in Chile, which has a 570 megapixel detector on it, essentially a very, very large camera, to observe tiny sections of the sky at a time, and then they jigsaw them all together to give this incredibly detailed image of about 1/8 of the total area of the sky, and in that image they picked out these 226 million galaxies. Now, why would you actually want to do this? What is the Dark Energy Survey for? Well, with a map like this of the positions of all the galaxies, you can get an idea for how galaxies are distributed throughout the universe, if they're clumped together, or if they're very smoothly distributed, sort of very evenly distributed, or if they're just completely randomly distributed. Now, we've known for a while now, for a few decades in fact, that galaxies are not evenly distributed. They're found clumped together in these big clusters and along filaments connecting those clusters, which gives us a sort of structure for the entire universe of something that represents like a sponge or a web. And we do actually refer to this big structure as the cosmic web. Now, it's gravity that causes that structure to form. You start with the superparticles after the Big Bang and they're all attracted to each other, and eventually you end up with this web-like clumpy structure. But the universe is also expanding, which means it's expanding the space between the galaxies. So especially between all these clusters and filaments, what we call the voids, they're all getting bigger. Now, the best theory we have of gravity right now is Einstein's theory of general relativity, which says that gravity at some point should eventually start to win against that expansion. It should slow it down until everything's just sort of nice and stable and balanced. But in the late 90s, we found evidence that the expansion of the universe is speeding up, not slowing down. It's accelerating. So that leaves us with one of two options. Either general relativity is not quite right. It needs some tweaking. And that wouldn't be surprising if that was the case. Maybe general relativity works on all of the scales we've been able to test it on in the solar system and in our galaxy and around black holes, but not on these huge, universe-wide scales that we're talking about here. Now, as of yet, no one has come up with a better theory of gravity that explains all the observations we've made. Now, that's not for lack of trying. There are loads of astrophysicists around the world working on these modified gravity theories, either modifying general relativity or modifying Newton's theory of gravity or coming up with a whole new theory of gravity. I've made a video on this before, which I'll link up here and in the video description below as well, so you can check that out. But because all of the evidence that we have points towards general relativity being right everywhere we've been able to test it so far, that means people have leaned towards option 2.
There is one other option.
That there's another unknown force in the universe that is always acting opposite to gravity. Now, we call this unknown force dark energy, but we have no idea what it actually is yet. All we observe is sort of the effects it has on our universe, causing the expansion to accelerate. And we can also work out by observing the cosmic microwave background that if dark energy did exist, then 70% of the universe's total energy budget would be in the form of dark energy. But to figure out what dark energy is and to test whether it exists, we need a big map of all the positions of as many galaxies as possible in the universe. With this map, we can then look at more distant galaxies as they were billions of years ago, so we can see how the structure of the universe has actually evolved over time, figure out what's causing this expansion, and therefore what dark energy actually is. This is what the Dark Energy Survey is trying to do, but just on a much bigger scale to greater distances than any survey has tried to do before. Not only that though, we can also probe not just dark energy, but another mystery of the universe, which is dark matter. So when we observe the sky with our telescopes, we're seeing things that either emit light, like stars, or block light, like dust, or reflect light, like planets and asteroids. What we don't see directly is therefore the stuff that doesn't emit light, or reflect light, or block light, or absorb light, but perhaps still interacts with light in the sense that it can actually change the path that the light takes. So in general relativity, gravity is described as massive objects curving space, and anything moving on that curved space has their path curved. And that could include things like planets, which is how we describe them on their orbits, but also it could include light. And how much the path of that light is altered tells us how big the object is. Now we can do this for big clusters of galaxies because we see light from background galaxies get curved and bent into these big arc shapes by the gravity of the cluster. When we do that, we find there's 6 times more matter there that we can't see than we can see. And at first people thought, okay, well maybe it's just all the black holes and the planets and the asteroids and the dust and the stuff that we can't really see because it's either a black hole or because it's so far away that it's too faint. If we take all that into account, does that give us 6 times more matter than, is in stars? And even with the most generous of estimates, it doesn't come anywhere close. So that led us to the idea of dark matter, matter that's like normal matter, except for the fact that it doesn't emit or absorb or reflect or block light. All it does is interact with light in this way through gravity. So we can also use this map of the positions of as many galaxies as possible to determine how the light is disturbed on its way to us past all the other galaxies in that map, to also figure out the distribution of dark matter as well as normal matter. So our current best model, our best theory to describe the entire universe is one that is expanding, that has gravity described by Einstein's theory of general relativity, that's energy budget is split and gone into creating about 5% normal matter, 26% dark matter, and 69% dark energy. This is what we call a cosmology. But we know there's big problems with this model, with this cosmology, because even when we try and measure something as simple as like the current expansion rate of the universe, we get a different answer if we use nearby objects to whether we use the cosmic microwave background, the echo of radiation left from the Big Bang, right? So this sort of tension between these 2 different measurements has been dubbed the crisis in cosmology, and I think recent events have definitely made those cosmologists reconsider what actually qualifies as a crisis, but it is something we want to try and solve to enable us to better understand, how the universe has evolved from Big Bang to what we see today. So the Dark Energy Survey and the scientists that work within it are hoping that with this new map of the positions of all the galaxies they have, we can essentially figure out what tweaks do we need to make so that our best model of the universe actually fits what we see around us. So that's why people got so excited this past week when the collaboration dropped the first 3 of 6 years worth of data and just made it all public, plus 30 scientific papers describing the analysis of that data and the initial results. Hence why it felt like Christmas come early for us astrophysicists and cosmologists around the world, right? Now, I thought about trying to get a video out dead quick last week, because it was like big news and it was all hitting the headlines. I was like, I've got to keep up with it. But I don't think that would have done this work justice. 30 scientific papers is a lot. And there's a lot of science in there as well. So I wanted to make sure that I truly digested it all so I could properly pull out the highlights for you, like the things that astrophysicists really care about from this piece of work. Now, most of these papers are a description of the data or their basic tests to prove that it's like consistent with other observations or, just showing that there's nothing glaringly wrong with it so people can really trust to use this data to do their own science with it now that it's made public. So a lot of these papers were just sort of confirming what we already know, sort of saying, okay, we've done this again and that's consistent with previous work, so we can trust this data when it tells us maybe that something else is different later on down the line. That will probably come, in a couple of months' time. More of the analysis will come, not just from the DES collaboration themselves, but from other astrophysicists around the world who now have access to this data. For now, though, there are a couple of things that I just wanted to pull out from these 30 scientific papers. The first is from this paper by Abbott and collaborators, which is essentially the entire collaboration. They have measured something called the dark energy equation of state. It's this little thing called W here. This is essentially the ratio of the pressure exerted by the dark energy divided by its energy density throughout the universe. Now, you'll notice that it is negative. Now, any W value less than negative a third means that the universe would be accelerating, expanding, essentially because you have a negative pressure, right? You're not pushing on something, exerting a pressure, you're pushing outwards on something. So what this paper was trying to do by measuring this W value was essentially determine what dark energy actually could be. And the value of W can tell us a lot about that. So for example, if W equaled -1 exactly, that would be the simplest possible form that dark energy could take. And it's often called the vacuum energy or a cosmological constant. What it means is that there's this dark energy density that's inherent in the fabric of space-time itself, the fabric of the universe, right? So it means that wherever you are in the universe, right, there's the exact same constant energy density. But of course, the universe is expanding and gravity is getting weaker as matter spreads out more. Those voids between the galaxy clusters are getting bigger. But as they get bigger, you've still got the same exact constant energy density wherever you are in that void that's getting bigger and bigger and bigger. And so this dark energy starts to outweigh gravity and it starts to accelerate the expansion of the universe. If W was greater than -1, then dark energy would be something else entirely. If it's around, -0.9 or 0.8, then it could be something called quintessence. This would be a quantum field that would permeate the entirety of the universe and generate this negative pressure that we know of as dark energy. But it would differ from the cosmological constant because it could actually vary with space and time. And because W would be less than -1, it would also mean that the dark energy density would decrease over time, and so that accelerated expansion of the universe would eventually slow down. For W less than -1, the dark energy density would actually increase over time as the universe expands, which makes no sense in physics at all. And so it was actually widely and largely ignored until about the early 2000s, when someone actually figured out a way it could be possible and sort of figured out the maths. And it was actually dubbed phantom energy, apparently because Star Wars, The Phantom Menace, had just come out.
That won't be necessary.
Oh, but it is!
If this was the case, that W was less than -1, and it was also constant, like it couldn't vary as well with space and time, then the dark energy density would just grow and grow and grow and grow with no bounds until, the entire universe, from stars, galaxies, even atoms themselves, would essentially be shredded apart in something that's been dubbed the Big Rip. Now, it seems crazy to think about that it's a possible end for our universe, that everything could just be torn apart. And so this is why we've been trying to measure W and the value that it actually could take. And over the years, we found that it's almost exactly -1. But what's interesting is that as we've measured it, it's sort of approached -1 from the less than -1 side, the Big Rip side. So back in 2004, for example, it was measured to be -1.02. The WMAP satellite in 2013 measured it as -1.084. And then the Planck satellite in 2015, -1.006 as well. So it's getting closer to -1 all the time. It's still not exactly quite -1. And again, it's coming from that less than -1 side, which is why I was so intrigued when I read the results from the Dark Energy Survey's 3 years worth of data that they've just released. And they measured W to be -0.98, obviously plus about 0.3 minus 0.2. So the uncertainties are probably still a bit too large to make any definitive conclusions yet. But if perhaps we had the full 6 years worth of observations from the Dark Energy Survey, rather than just this first chunk of 3 years that they've released today, then we'd have a larger map, probably a larger area of sky, more galaxies, and probably able to drill down those uncertainties more so we can actually determine what form does dark energy actually take. The second thing I want to highlight is what, all major media outlets went with, right? That dark matter is distributed through the universe a lot smoother than we thought. It's not as clumpy. However, I want to rein in the people who write headlines at the minute, because I want to point out that the thing they've actually measured, this value that they've been able to put on the clumpiness of dark matter, which you can see in this abstract here, is called S8. That value is lower than the previous measurements, yes. So they've found here 0.772 plus or minus about 0.18. The Planck collaboration in 2018 found that their S8 value was 0.827 plus or minus about 0.18 again. And yes, while those uncertainties don't overlap, and that is very intriguing, they're not different enough to be what we call statistically significantly different. They're not different enough that random fluctuations in the experiment couldn't explain those differences, right? They're not different enough that you start being able to confidently state that the statistics back you up to make a claim that one measurement has, got it wrong. So I think these big, bold headlines were a little bit misleading. But what have they actually measured here to get at this clumpiness of the dark matter, this S8 parameter, right? This is actually something we call cosmic shear. So this is the distortion of the images that we take of, very, very distant galaxies that's due to the fact the light from them is distorted as it travels through and past this large-scale structure of the universe, this cosmic web. Now, it's not as dramatic as what we call strong gravitational lensing, where you get these single galaxies distorted into these huge arcs as the light travels through these big galaxy clusters of stars and dark matter. You have to have perfect alignment for that. Instead, we're looking at something called weak lensing, the little distortions that cause a galaxy to look elongated slightly due to its light sort of just skirting by this huge big web-like structure of galaxies and dark matter. For example, I can create the same effect with a wine glass, right, and a candle. Perfectly aligned, I get these strong arcs and can even get a ring if I get it in the exact right place. If I offset it slightly though, the image of the candle is still disturbed, but not by much. These distortions let us map out where all the matter is in the universe that's causing these distortions. And we can obviously then compare that to the map of all the galaxies and the stars, the visible stuff we see, take one from the other, and then we get a map of where all the dark matter is in the universe instead. We can then compare that to the simulations that we run on computers of the structure of the universe forming and matter clumping together when we put all the known laws of physics in, like gravity. Any differences in the distribution, whether it's smoother or it's clumpier, means we've got something wrong in the simulations, i.e. we've forgotten some law of physics or some component of the universe. So because the results from the Dark Energy Survey are suggesting that dark matter is distributed smoother than we thought, this means that there's probably something wrong with our cosmological model that we had before. And again, the most likely candidate here is that Einstein's theory of general relativity is a little bit wrong. Again, works great on the scales we've been able to test out, solar system, galaxies, but these larger scales that govern how the structure of the universe forms, it might need some tweaking. I'm not talking about the sort of rip it up and start again kind of thing that I was talking about before, because it can't explain why the universe is accelerating, expanding. For that, we still need dark energy. This would just be a little tweak on the larger scales. To find out more about this study on cosmic shear, though, I called up my colleague on the Dark Energy Survey, who was actually lead author on this study, Dr. Alexandra Amon from Stanford University, and I called her up to chat all about it.
So I work as part of the Dark Energy Survey, which is a large international team. It really is an enormous effort of mostly young scientists. And my role was in leading this cosmic shear paper, which is the measurement of weak lensing due to the large scale structure of the universe. weak lensing is extremely powerful for cosmology, but it is a very challenging measurement. And that's because we're measuring the shapes of these very far away galaxies. And you're probably imagining a very beautiful spiral image. And well, we just draw a circle and measure shape around it. But what we're really working with are these fuzzy blobs in our images. They're far away, they're a few pixels. Some of them are sitting on top of each other. And we need percent level or precision measurements of the shapes of these galaxies, which is extremely challenging. So for weak lensing, you need a large sample because, as you said, the measurements are so small that you wouldn't see the lensing effect on one galaxy. You wouldn't be able to tell the difference with your eye. But when we look at a sample on a statistical level, when we have 100 million galaxies, then we start to see these trends and these alignments and changes in shapes form some kind of pattern on the sky.
So why is this measurement of shear so important? You know, there's so many things that have to come together for you to do it. What can it tell us that's so important for our understanding of the universe?
Yeah, that's a great question because we have so many different cosmological probes that tell us different information. So what does weak lensing bring to the table that we don't already have? So we have exquisite measurements from the cosmic microwave background made by the Planck team, for example, but they are probing a very different universe. They are making measurements of our universe when it's just this soup of particles, rather than what we're measuring with weak lensing, which is our late time universe, or the universe that we're more familiar with, where you have galaxies and stars and clusters. So really these two measurements together, these two types of measurements from the early universe and the late universe is what's most powerful, because when we compare their results, we're testing our standard model over cosmic time. So we're seeing if our one model that we've come up with works for 13.8 billion years of expansion of the universe. So it's the most beautiful and the most elegant test that we can create by comparing our measurements to the early universe.
I mean, this paper, I think, got quite a lot of hype, or at least the whole 3 years worth of data dump that happened last week got a huge amount of hype in the media. And one thing they picked up on was these cosmic shear measurements showing that dark matter was smoother. Obviously, in the paper, you're very clear that, like, there's no statistical, like, difference between this measurement and the previous measurements. So, like, no statistically significant difference. Like, it's like, well, like 2.1 sigma or something. Like, how sort of excited or reined in should we be, do you think, about the fact that the measurement that came from DES was different to previous measurements?
Yeah, that really is the question. Is this exciting, or is this level of tension exciting? I think I will say the word unfortunately, that with the dark energy survey, this was the data set that could tell us, you know, we have unprecedented power, but our measurements kind of fit exactly in a way that it is low compared to what Planck predicts, or it is a smoother universe. It's kind of annoying and tantalizing at the same time. We see something there, we haven't been able to answer for sure. Is it totally bang on what the early universe gets, or is it way off? You know, we're still sitting in that middle ground that is difficult to understand from DS on its own. What will be most interesting is being able to work with the other surveys to combine all our data sets and do a joint analysis of all three. And I think we'll really have the power there to see it, you know, to make more of a concrete statement about this tension.
Do you think when the 6 years worth of the DES data dump comes, like in, I don't know when that might be, you probably can't tell me, but whenever that does come in the next couple of years, and that's going to be the full data set, do you think that will tell us or allow us to figure that out, or I guess you've got your fingers crossed that is what's going to happen?
Yeah, so we have that data in the can already, and we've already started making our catalogs and doing the analysis. There's no time wasted. It's interesting because we're doubling our data set. And it is challenging because, unlike the jump from year 1 to year 3, we're not growing in area on the sky, but growing in depth. So the year 6 survey is twice as deep. The images are twice as deep.
So you'll get more distant things.
Yeah, and that is extremely powerful. So it's letting us look at galaxies further away, so we can see that evolution of structure more. But for the measurements that I was talking about, these measurements of shapes and measurements of redshifts, it makes our job a lot harder. So all of our methods will be pushed to the limit to be able to analyze this deep data.
What do you think are going to be the the big things that change our understanding of cosmology in the next 10 years? Or maybe even just confirm that, no, we had it right. What's going to be those things, do you think, that are coming up? Like, what should people look forward to?
What I'm most excited about is seeing all the different fields merge. So we're already at a stage in our DES Year 3 results. For example, in my paper, we do a little analysis at the end, trying to figure out what's limiting our measurements. Do we just need more data? Do we need to understand different modeling aspects? Or are we not calibrating our redshifts, our distances well enough? And what we find is that we're theory limited. So we are limited by our uncertainty in modeling essentially galaxy formation. And that's exciting because galaxy formation on its own is exciting, but also because, we really need our fields to start merging. For lensing, we need to be able to understand baryonic effects, and feedback processes. And we need to be able to understand intrinsic alignment. So how much galaxy shapes are correlated just because galaxies live in the same area of the sky, not due to weak lensing. And as I said, galaxy formation on its own is interesting, but how interesting will it be when we all need to understand each other's research well enough to work together? So combining CMB measurements with weak lensing measurements and combining galaxy formation expertise with cosmology. In that frame of thinking, especially if you have 100 million galaxies, they aren't galaxies. They're kind of just a number, and you're measuring things from them. And now when we talk about combining like your expertise and my expertise, you have to think of them as galaxies, and you have to understand how they work. Otherwise, you won't really be able to use your data. So,
and that is a scary thought. Lots and lots of data sat there unused. I think that's the scientist's worst nightmare, right? Like, thank you so much to Alex for taking the time out of her day to chat to me about all things at Cosmic Shear. If you want to hear more from Alex, you can follow her on Twitter at AstroAlexAmon, or you can follow her on Instagram. It's at AstroAlexAmon. And I'll be posting the full version of our chat, because we chatted for much longer than that, on my channel on Sunday, so look out for that. So I hope that helped you understand this cosmological Christmas at Come Early that we had this week. I'm obviously very excited to see what results are going to come in the future, not just from the full 6 years worth of data that they'll hopefully be releasing very soon. This was just the 3 years that they've been teasing us with, but also the results that will come out from the collaboration and from, the wider community now this data has been made public as well. And you can bet when those results come out, I'll be chatting about them in my monthly Night Sky news videos, so make sure you look out for those. For now though, we just have to be patient as people take great care in doing what is very, very difficult science. But we can rest assured that some answers, and let's face it, a whole host of other questions, are definitely on the way. I didn't record any of that, did I? Stupid mic. I didn't even check. Sticks. I hate myself. I hate myself. I hate myself. I hate myself. With 5% of the universe's energy budget going into dark matter and space is hard. Words are harder. Like a damn cosmologist.